honest, I am going to go through the number 20 homework problem. So we have here a lot of information, and that is part of what is challenging about this problem. It's just information overload. So I've started it by looking through some of the key pieces here. So it says angle A is the vertex of an isosceles triangle. So first, I would take that and think, what does that mean for what we know to be congruent here? I know AB are going to be the legs since the vertex is A. That means the base congruent angles will be B and C, angle B and C. So we've got this here. So going into the problem, it is helpful to know that AB and AC are going to have equal measures. And then angle B the measure of angle B is going to be equal to the measure of angle C. That's important here. So let's see how that ties in here. Next up, it says that the number of degrees in angle B is twice the number of centimeters in BC. So that would mean that angle B is going to be twice 2 times BC, its measure here. And the number of degrees in angle C is 3 times the number of centimeters in AB. So the measure of angle C will be 3 times the measurement of AB. And when it says centimeters, it's just that's the measure of it. So it's length in centimeters because the units for angles are degrees. So it's different units, but you can take their numerical values and compare them like this, twice and 3 times ratio here. And then it says that angle B is x plus 6. So that is something I'm going to write in this diagram here. And C is 2x minus 54. Okay, so now here's this, and here's what we have. And there's ways that you can start working this through, and you can keep labeling your diagram, or you can mark this off to the side. One thing that I notice here, once I fill this in, is that these angles are congruent, which means that x plus 6 is going to have to be equal to 2x minus 54. That's what it means for things to be congruent. They have equal measures. So this is exciting because we can solve for x. So working here, that makes x plus 6 equal to 2x minus 54. So let's do some solving here. That makes negative x equal to negative 60. And flip those signs, x is equal to 60. Okay, so here's the thing. Now let's see how this is helpful. So going back, x plus 6 is 66 degrees, and they should be equal. So let's see here. 2 times 60 is 120, minus 54 should be 66. Let me think here. That's 70 minus 4. Yeah, so that's 66 degrees as well. Okay, now we've worked some stuff through. We are asked to find the perimeter of ABC. So now the information that's highlighted in the initial problem connects angle measures two sides. So the measure of angle B is twice the measure of BC. So that means it is going to be a bigger number. So now is where there's not as many equations you can really set up here. More would be a reason through the idea that that means that the measure of angle B is going to be, segment BC here, if you were to solve it, is going to be half of the measure of angle B. So divide that by 2, that makes BC 33 centimeters. So that's getting us somewhere. Next up, we have that angle C, 66 degrees, is 3 times AB. Well, if we have 33 equal to 3 times AB, solve for the length of that side, divide by 3. That is going to make AB, oh wait, why am I saying 22? That should be 11. Oh wait, that's the wrong measure. I knew that was wrong. 66 is the angle. Sorry, let me go back. 66 degrees is the angle measure. Divide that by 3, that is 22. So that's going to make this guy here 22. Last but not least is that third side, AC. The problem didn't tell us any information, but hopefully you can see here it is a congruent leg. So that is also going to make it 22 centimeters. So we have all three sides. So that makes our Perimeter 33 plus 2 times 22, so plus 44. That is going to make this 77 centimeters. So that is how this works out from here. I am going to next in this video go through the problems I had mentioned from the notes. And if you have questions from there, email me, come see me at office hours. All right, as promised, we're going to work through the last couple of problems from the notes. So I've set up here one. If you look at this proof, you're going to notice it's a little bit different. There is an error where the angles you're supposed to prove congruent are the right angles that didn't get changed from last year. So let's go ahead and instead change it up. I also removed a given. So this is what we're working with. A circle, two right angles. We're proving ST congruent to VT. So where does HL congruence come into this? As you look at this problem, a couple things that I noticed. One, if you were to draw in PT, and then there is a step that we do want to add in here, that is something I do want you to have as a step in your proof. So this was an old one that I had copied, so let me move this and add it in here. So let's say that we call this our step draw PT, and our reason was auxiliary line. And then we know it's congruent to itself by reflexive property. And if we think in terms of a right triangle, this is the hypotenuse of both of those triangles. So we've got an H in HL congruence. Then PS is congruent to PV. Those are both radii. So if radii, then congruent, or all radii are congruent. And then, again, it will carry over from last year. This should be HL congruence. Now we have a pair of corresponding legs congruent, the hypotenuse, and we know that we have right angles. So that is going to make these triangles congruent by HL congruence, which now, as you might have supposed, we could prove those two segments, ST and VT, congruent by CPCTC. So this proof here has 5 steps, but I hope you feel that the logic of this is more straightforward as we're looking at our pieces and looking at the ways that they come together. So that is proof number 3. If you still are confused, go back, rewatch this again. Let's go ahead and look now at number 4. So number 4, to save time, I have already marked everything. And then we have our givens. We know that because they were given to us. If you need to mark everything and take a look at this proof before you listen through the solution, pause here, watch it, and then start it again. So here's what I'm noticing. My goal is to prove JD, which is this whole segment on the side, congruent to HE. My mind is wired for triangles. I don't know about yours, but that is how I start to see things. So I think about, okay, I have my perpendicular segments that make right angles. And let's go ahead and state those, see if we want to use them. So that was angle DJF and angle EHC are right angles. And this would be, if perpendicular, then right. All right, so I do know that. I know that CD is congruent to EF, so these down here. And then I know these segments here. Thinking in terms of right triangles, do I have enough information for HL congruence or any other way to get there? Because if I prove these two triangles congruent, you might be thinking, there's a lot of triangles going on here. What are you talking about? This is a nice, sorry that it moved there, place for overlapping triangles. Let's follow segment H or CH. That's here. Let's follow the right angle. That takes us down here. Then let's connect those. That is going to be this triangle here. Hey, guess what? We already know a lot of information about this triangle. We have a full side and an angle. If you're looking at my little butterfly triangles, again, don't have a lot of information about those triangles. Can't use vertical angles because we don't know anything that they're congruent to. So it's just this triangle, and it would correspond with, let's follow JF. JF is here. Oops, that didn't work. JF. Let's go through then to JD. And then back here. So here's what we got. We currently have a full leg on each of them that are congruent and right angles. Where is the hypotenuse? It is CE and it is DF. They currently are not congruent, but how could we do that? If we look at this little part, if I added DE onto it, that forms CE. If I took DE and added it onto EF, that forms my hypotenuse DF. That is addition property. So I could prove hypotenuse CE congruent to hypotenuse DF by the addition property. And look here, now we have HL congruence. We have the hypotenuse, we've proved them congruent. We've proved one set of corresponding legs congruent, and we have right angles. So I can prove triangle JDF congruent to triangle, so JDF congruent to triangle J to D, H to E to C. Take some time. Even with that one, it takes me time to figure this out. And this was HL congruence. The right angles were step 2. My hypotenuse were step 3. And my legs were 1, 2, 3, 4, the fourth given, so we could call that G4. Okay, can I use those congruent triangles to prove JD congruent to HE? Absolutely, those are corresponding sides. So step 5 would be JD is congruent to HE by CPCTC. So there's another example of some overlapping triangles, but don't fully overlap. How this works here. Let's look at one last example, and then that will be the end of these notes to help you out here. For number 5, we have, I've marked things already too. We have GT is congruent to HI, or sorry, GT and HI are altitude. So I marked right angles at their intersection points. TH is congruent to IG, so I marked those congruent. And I'm trying to prove that HXG, this triangle here, is isosceles. Using my instincts, I'm going to mark with question marks the sides I think would be congruent, which I think would be these, and I think my congruent base angles should be these guys right here at the corners. So, is there a way we can make connections to prove that either those sides or angles are congruent? Well, I know our first instinct is to look at these little X butterfly triangles here. I have a right angle and a side. I have vertical angles. So if you wanted, you could prove these vertical angles congruent. And look at the order here. That's an angle, and a side. So you could do angle, side congruence. If you saw that first, that would be we have our givens. So what do we need to do? We have the sides proven. We need to prove those vertical angles and prove those congruent right angles. So with the right angles first, that would be angle XTH and angle XIG are right angles. So it'd be if altitude, then right angles. And then we can prove them congruent. So here we actually need to prove them congruent because we're using them not as just a right angle, but as a set of congruent angles. So to XIG. So that would be if right, then congruent. And then the next thing we would need to do would be to prove my vertical angles. So angle TXH is congruent to angle IXG because vertical angles are congruent. And that would allow us to prove these triangles now. So that's THX is congruent, these are weird letters, to IGX by AAS congruence. And how does that help us? Well, the two sides of my isosceles triangle are two corresponding sides of those triangles. So we could do XG, or sorry, no, that works. XG congruent to XH by CPCTC, and then use that To prove that triangle HXG is isosceles, this would be by if we have congruent legs, then we have an isosceles triangle. So I wanted to point this out because a lot of you want to make it work with the inside angles. This would be, with those inside triangles, this would be a case where it would work. Now, in the context of HL congruence, you also, I'm going to do some erasing here, could prove my overlapping triangles, THG and IGH, with reflexive property and HL congruence, and CPCTC is going to give us our base angles, which would give us our legs, which would make it isosceles. So that is another option for you to look through here. So those are our problems. If you again want to see any more, rewatch it. If you still have questions, send me an email and I can help you out from there.